Hello, everybody. Today, I'd like to talk to you about an issue that raises with the rising adoption of generative AI. We are gonna see what happens when you feed a model with its own output, and we are gonna see how the model behaves iteration after iteration. But to understand why this issue is actually relevant, I'd like to start with a fireside chat with these two young men. Of course, everybody of you knows them, and they were speaking at LlamaCon less than 6 months ago about the adoption of Gen AI inside their companies. And Satya Nadella told Mark Zuckerberg that up to 30% of its company code is actually written by AI. Up to 30% is a big percentage that is raising and raising over and over again. And similar statements have been done by Google more or less a year ago and are actually being made by many, many companies inside this tech world. So this is a kind of example in which we see how Gen AI actually impacts our daily life and daily jobs. So we can now understand what impact maybe have a particular pitfall in this kind of models if they are not trained properly, and they may affect our future models. So to dive inside this kind of topic, I'd like to start with you with a small story. So let's say that you are a data scientist and you want to train a Gen AI model to generate images of birds. So what you do is to take your data set, and the data set is, can we say, a big data set of birds in various aspects, in many images. And then you take an architecture and you start training. So you feed this architecture with the natural data, and you obtain a good checkpoint from your PyTorch model. So now that you have this model, you say, okay, but this model is behaving properly, and its generated images are nice, and I like those. So why cannot I ask the model to generate other images to maybe train another iteration of this model? And you do this. So you obtain another artificial data set, you feed the model with this kind of images, and you do it more and more times again, iterating on its own output. Okay. The results, at a certain time, you decide to look at these results and you end up with a fish. Okay, so you are not so satisfied anyway. You were looking for birds, not for fishes. But what happens under the hood? So under the hood, it happened that iteration by iteration, your model slowly loses some particularly spots of the birds, such as the feathers, for example, and it starts hallucinating new details, such as the fins of the fishes. So the model does not suddenly change from a bird generator to a fish generator, but it starts in this iteration to behave not as expected. And in practice, coming outside from this artwork and going to our pipeline, what happened is this part. So you start with real data on which you fit an actual model that is a generative model. Then you sample from the model, you ask the model to generate brand new data. Then you feed those data, only this data, to the new model that is the next generation starting point from the previous one. And you go on and on this way until they complete the generation. But you know, this is the glimpse of what we are going to see. But when I started looking inside this kind of topic, my journey started from a particular paper. This particular paper, written from a researcher in Stanford University and UC Berkeley, is one of the most important papers in the field of what we call model collapse. And this researcher started from images as well, training a stable diffusion model. So they trained a stable diffusion model on only natural images and asked them to generate an elderly woman writing in a journal in a charming village square. And this is what they obtained. So you see that the woman is kind of realistic, even if it may have some slight differences from the real reality. But this is something that we would accept as an output from our model. Then they asked to do the same outputs, but instead of using 100% real images, they decided to have a mixture. And after 5 retraining iterations, they started using 70% real images and 25% of generated. And the result was this one. So this is actually not what we'd like to have in our design papers, in our presentation. Is not what we ask a model to generate. Imagine you go now on Gemini or ChatGPT and ask for an image of a woman and you obtain something like that. You are not satisfied with this kind of outputs. But this does not happen only with images. This happens also with LLMs, since other researchers tried to do the same experiment, but working with LLMs, and after 9 training iterations of an OPT, they obtain this kind of outputs. And now, even if you don't still read everything of the prompt and the generation, in the generated text, you see that you have all these kind of repetitions, all these kind of add symbols inside the text, and this is not surely what you were intended to have. So now we already have a kind of idea of what model collapse is, but we also have a definition provided by those researchers. Since this model collapse is a degenerative process affecting generation of learned generative models, where generated data end up polluting the training set of the next generations of models. This pollution may have the effect to make those models misperceive reality and then generate something that is not actually what you intended them to do. And what happens is that you start from the data with finite sampling. You sample something from this data, but of course probable events are overestimated and improbable events are underestimated. And after this sampling, you have to fit a model on that. But of course, each fitting is an approximation of the original distribution. So you add new errors to the pipeline. But let's start trying to have in mind what finite sampling is. So let's say that you have to fit a Gaussian distribution, a normal distribution. So this is what you want to estimate. Of course, in real life, you don't know which kind of distribution you are fitting. So this is just a simple toy example to have a kind of idea what's happening. So iteration after iteration, so estimation after estimation, the generated distribution ends up to be not the same as you started. And this happens due to oversampling in the probable part of the distribution and undersampling in the less probable sample of the distribution. So you see that tails are shrinking and every part of the distribution is collapsing towards the original mode of the distribution. And this collapse to the mode is also seen in practical examples. So for example, here, the researchers trained a variational autoencoder with only 100% of real images, or after 20 iterations of 100% of generated images. And you see that on the other side, on the generated side, you have more or less always the same image. And coming to the approximate fitting can be explained like this. So you start with a more complex distribution, and of course, every model has to be simpler than the original data distribution. So what's happening is that you are starting to have, for example, this kind of model that fits your data. Of course, this is simpler because it has a single mode instead of two. And what happened here is that you have the artifact creation. Since you don't have any data in the original distribution in that part of the variables part, but now here is where your distribution puts most of its weight, its samples. So artifacts and mode images can be seen combined in something like that. So the researchers show that with the 50% of real images and 50% of generated images, or with 100% of generated, you have this kind of conversion of iteration by iteration. These older Hispanic men become similar from iteration to iteration, and you have those artifacts on the skin of the man and on the background. So you can see that now we are having a model that should be better since it is enhanced by new data rather than only the original one, but actually this model is getting worse and worse. So what can we do? Can we have an idea to heal this kind of problem? Well, let's start always also with this example of the older Hispanic man, and let's start with this blend. So we have 70% of real images and only 25% of generated ones. And let's say, okay, I already have the collapsed model, but if I put new data, new original data, real images to my training set, can I heal this issue? And the answer, sadly, is no. Since in reality, some artifacts in the background kind of disappear, but actually the face of the man is quite similar to the previous iterations, and still we have artifacts on its skin. So retraining appears not to be the solution to our problem. So what about watermarking? So we can decide, since models are already affected and we cannot recover them, let's work on the data. So let's say, okay, this data is AI generated, so I don't want to use this data for my future trainings. So I put a watermark on that and say, okay, this is AI generated, don't scrape it, don't use it. And this is something we are already seeing mainly for the copyright part, since many websites are adding some files to avoid scraping. But the content can also be watermarked inside thanks to many algorithms. For example, SynthID or Video Seal from Google, Meta, and other big tech companies. But this may be still up to us. So I have to decide, okay, I want to watermark that this is an AI-generated content. And while I was studying for this topic, I ended up more or less here, and I said, you know, I am a bit discouraged. So is really our AI world going to a bad end? Is this our future? And in reality, I found new results that gave me a bit of hope, and I'd like to share those with you. So, for example, this is the setting that we were talking about since now. So what happened is that you take the data, you train a model, then you generate this new data, and the next model just uses the current generated data. It discards all the previous one, like they were already used, so they are not needed anymore by the second generation of model. But in reality, when you think about building up a Gen AI model scraping from the web is filled up with natural data and generated data. So the real setting probably is this one, in which you don't substitute the data set, but you add the data set and enlarge the data set each time with new data generated, of course, but new coming from new sources without discarding everything that happened before. And in this new setting, actually, things change. Because it has been proved that in linear and in logistic models, for example, while in the substitution framework you have an unbounded test error, on the other side, in the accumulation framework, you have an upper bounded test error that is upper bounded by a constant. So starting from the second iteration, so quite soon, the accumulation setting is way better than the previous substitution one. This is for the linear and logistic model. It has been proved mathematically, but also other topics, other frameworks can have this benefit. So for example, variational autoencoder for image generation more or less seems to behave similarly, since you see that the loss of the test set on the left side is raising with a high level of slope, while on the other side, more or less, the slope is clearly the same. And this happens also for other topics, such as diffusion models and other models. But this is not the end, because Google, a few months ago, published this paper, Escaping Collapse, in which they then proved that we also have a procedure that we can use. It was developed for LLMs, but also for other topic can be used, of course. And this procedure can be used to not only avoid collapse, but also get better models. And the procedure is this way. So let's say that you have a prompt that you want to label to train the next generation of an LLM. You have draft LLM, let's say, and you ask to this LLM to label this prompt for k times. So you give the prompt k times to the LLM, and you get k different responses. Of course, this happens because LLMs are not deterministic, and also you have some parameters like temperature that you can tune to obtain different responses. Now, you have those responses, and you want to have a quality check on that. So you perform a quality evaluation step, and here the quality is intended as binary. So in this paper, quality is either 0 if the response is not good for the prompt provided, or 1 if the response is proper for the prompt. This can be, in particular, good for deterministic tasks, such as coding or mathematical questions. But in the next studies, they are planning to make quality also continuous. Now you have your responses with the quality evaluation, and you take the best response set. In the best response set, you have the prompts and the best response you have. The best response can have, of course, value quality 0 in case no response has been perfect for the prompt, or 1 if at least one response was good for that kind of prompt. Once you have this response set, you divide the set into 2 parts. The low quality prompts, so the one that gave you 0 in the quality evaluation, and the high quality prompts and responses, where goes every prompt with its responses that had quality equal to 1. Now you take the low quality prompt, and you pass them to a beta weak labeler. This step has to label at least beta prompts correctly to your purpose. In this part in particular, they said that for now, this step has to be performed partially by a human in the loop. But it's not compulsory that this still hold in the future. This percentage beta can be small enough, but it's enough to get the improvement of the model. Now you have these weakly labeled prompts, and you put all them together with the high quality prompts and responses that were a part in this previous step. Now you got a weighted mixture depending on some parameter that you choose, and you have a new training set. With this training set, you train in the next generation of the same LLM, and you start again with the prompts, the responses, and so on. Well, their paper proved that this kind of process converges to an optimal LLM, not just to a good LLM, but to an optimal LLM. So they first took away the model collapse issue, and then they are also improving the models as it was their first purpose. After this result, I was more happy and more trustful in the next generation of LLMs. And I started thinking that maybe starting from a bird, we can end up with another bird. These are some of the resources you may be curious to read for this talk, for your getting deep inside this talk. And I am Valeria Zuccoli. I am a data scientist in Intella, where we build software for in intelligent satellites operation. Feel free to reach me out on LinkedIn, and hope you enjoy this topic.
Thanks a lot. Questions?
Thank you. Nice reminder about the dangers of not understanding what you sample from and how you sample. So it's a very nice reminder. I just have it may be a stupid question, but in the beginning you said that there is like, you made an example about how much percentage of code is being generated.
Yeah.
So I'm just wondering, like, how do you connect that with the rest that you talked about? That's why I say, maybe this is a stupid question, but I just didn't get the kind of connection.
It was just to raise the attention to the meaning that we are using AI, Gen AI in particular, every day more and more and more. So if the 30% of the code is AI generated, it may end up in the next training set for the next co-pilot. So the issue is relevant also for this part. So everybody of us probably use any kind of Gen AI model in its daily life, and their results, their output can be part of the next generation of sets.
Understood. Thanks.
You're welcome.
Other questions? Yes.
Thank you for your talk. If I understand correctly, the solution you propose is that we should keep a clean data set that we use at the beginning and to evaluate on it. How can we do that? I mean, for historical actors, I guess, if they are aware of what you presented, they have at home a clean data set, but for exterior people who might want to start after, because the content that we scrap today on the internet, it's already polluted.
As you got, the data curation is one of the main takeaway of this talk. So I've not found many results on how to behave properly in data curation. I believe that most of the job is up to us, even for the watermarking, for example. Our collections of data sets is something that we have to care of. And that's depending on having the right sources, so ensuring enough diversity of the data set, because we can also have in data set of real images, but if they are only of, how can I say, bluebirds, our generated model would just have us to bluebirds. So it depends on what is our purpose, but data curation is very important, and it's up to us depending on our purpose. Diversity first. Diversity first.
We have time for a few more questions.
Hello, thank you for the presentation. So if I understand correctly, in the example you gave, we keep feeding the same model with data generated by itself. Would it be different if we fed another model, maybe another architecture, but that takes the same kind of input and output? Or is it just a matter of time that we will pollute all the models anyway?
Okay, nice question. I also asked myself the same question as I was preparing the talk. Well, in reality, it doesn't matter. It's not very different. So it's probably just a matter of a few iterations. But actually, the reality is so complex that probably no model can fit it perfectly. And so you are spreading error. So you are maybe spreading a different kind of error, a different distribution of error if you take the generated data from another model, but you are still shrinking the tails anyway, because each model does that because of the constraints of the model. So I believe it's just a matter of time, sadly. if we don't curate enough our data.
One last question. When it's me, what the L is about pi2/6? Where is this coming from? The pi2/6?
Oh, okay.
Where is this coming from?
This comes from some formulas taken from a paper that provided the actual demonstration of this bounded or unbounded test error. There is the mathematical proof in the paper that is called universality of the p²/6, actually. And yeah, that's coming from a mathematical proof.
Okay, I'll check it out. Thank you. Thanks a lot.